Hello students, in this module our target is to derive the expression for probability of error for the optimum multi-user detection. So, this is in continuation of the last two module where we have discussed and understood the concept of the optimum multi-user detection mechanism, and we have also seen the receiver architecture where the optimum how the optimum detector is devised and how it is working. Here actually we have also understood that the efficiency of our detector, optimum multi-user detector, is given by the complexity involved with respect to the total number of the users present per bit, and it is the total complexity involved in the detection per bit, and basically its expression is given by the total complexity involved per bit given by the total number of the users. And here actually in some other way we will try to do the performance analysis of these optimum detectors, which will be the probability of error computation. Remember one thing, that the whatever the detector architecture we do, whatever the receiver architecture we propose, finally our target of the interest and our point of interest in any receiver architecture design is the getting a minimum error probability. You minimize the error of your decision process and try to detect the transmitted signal as perfect as possible. So, what is the error probability? Error probability calculation is a very important parameter and very interesting parameter for all the system engineers. The error probability here in the multi-user optimum multi-user detector situation, we will be actually defining the parameter as pk sigma, and where the k is indicating the number of the users over which actually you are carrying on, and the small k can vary actually for the whenever we compute the minimum error probability, it is associated with a typical user also. So, this k parameter is actually varying for the user to user, and in presence of the noise actually it is important. So, its noise the variance of the noise will be sigma square, and so pk sigma basically in presence of that noise you are trying to identify. So, the fundamental quantity of this minimum error probability is achievable by a receiver. With the receiver, I understood that the receiver structure is like this, where we understand that for k number of users are present in the channel, and each of them are transmitting transmitting their corresponding signal bk I should say, with their unique signature waveform Sk associated with it, and Ak is the received amplitude of the signal associated with the kth user. And we have considered Nt continuously over the last two modules. The Nt is a Gaussian noise process associated with it, and in the single, suppose if I see that this is a very generic model at the front end of the CDMA receiver in a multi-user scenario. If I consider the fact that we have only a single user, so this summation goes off and you are ending up with a yt is equal to a1 b1 s1 t plus nt sigma nt, and in that case we understand that for a single user the minimum bit error rate or minimum bit error probability of getting minimum error which is governed here by p1 sigma can be given by a q function of the SNR involved, where a1 is the amplitude you have estimated, you have received from that user 1, and this is the noise power spectral density sigma is about. This expression is very well known expression to all of us, because we always deal with this situation for a conventional user where conventional receiver where multiple user concept is off. If I extend it now for the k user channel, so then we understand that for the kth user you will receive the interested part of the signal related to the kth user, and also you will receive the interference from the other users and also the noise associated with this kth user. And so, if my that rho jk, and rho was what? Rho was our cross correlation between the two signature vectors, two signature waveforms, and if rho jk is equal to 0 and for k not equal to 1, then actually this will also, as long as this the same conclusion we can obtain. I mean, this whole part will go back and you will get for the user 1 again for the error rate is equal to error probability will be given by this, because if the rho is 0 perfectly, that means the signature vectors are aligned to perfectly orthogonal to each other, then the contribution from the second part of this expression 1.2 will be completely 0, and you will be ending up with the expression equivalent expression of 1.1, and hence your error probability will be governed by this. In practice, that is not the case. In practice, you have to deal with this whole expression where sigma k, where the rho k will have some specific value between 0 to 1. And as long as this different transmitted information vectors, I mean B1 to Bk, that are coming from the different k in different users, they lead to different received signals. We have actually that rho k is equal to 0. But remember one thing, this is very unlike expression that we have received for this multi-user detection scenario. We never get actually in a single user match filter, because single user match filter output will never give actually with this properties does not hold good for this single user match filter, because there it can give actually some hypothetical scenario if something happens that the background noise is totally absent, but still it will give at the output, the match filter output will give some error, it will generate some signal at the output, it may generate. So, single user match filter output can never ensure you that you will get the pk 0 is equal to 0 when my noise variance is completely 0. So, computation of this error probability calculation, we will start with a 2 user case, because it is easy to track and easy to understand whether, and in future it can be extended also for the k number of the users. We will refer again to this diagram that we have seen in the earlier discussion, and we understand that referring this decision regions of this minimum error probability detected in this figure, in order to compute the error probability, it will be for user number 1 same. It will be fundamentally to devise the conditions on each of these 4 possible transmitted bit pairs, such that basically 4 possible transmitted bit pairs, and then you compute the probability that the received vector will cross the boundary of this decision zone when other part is transmitted. And once we try to do it, then it involves actually integration over the 2D Gaussian distribution, and on a subset of this plane, and which cannot have any closed form particular structure, and therefore, we cannot have any closed form expression for this integration over the 2D Gaussian distribution, and hence we cannot actually come with a nice expression, closed form expression, for example, in terms of the Q function in such scenario, if we involve this 2D Gaussian integration over the 2D Gaussian distribution. So, we will try to do what? I mean, instead of showing something that does not have a closed form expression with a known form of function like the Q function, and which has actually finally solution is there, because if you are not having any closed form expression, you can solve that equation by numerical optimization, or some numerical solutions are available, not optimization, numerical solutions are available for that expression. But better approach may be taken by providing or trying to find out the lower and upper bound of those expression, such that you can understand the performance of such detectors will be bounded by this region. So, error probability can never go beyond these levels, or cannot be improved below this level. So, upper bound and lower bound we will try to find out now. So, let us start with, and we continue the analysis with this jointly optimum decision strategy, and referring this decision minimum distance decision regions that we have seen earlier. that the minimum distance detector makes an error in identifying the B1 as this. So, P1M is actually PM stands for the minimum distance detector, and actually it try to find out, it try to detect a signal by minimize where actually the distance is minimum. That is the fundamental is about. So, the minimum distance detector given by PM, if it is a user 1, confined to user 1, that is the meaning of P1M is in presence of the noise. Sigma is the power spectral density of the noise we have already considered. So, that error can be written like this. What is this form I have written is 1/4 is the possibility that the probability 1/4 time the probability is that you have transmitted both the signals +1 +1, I mean B1 and B2 transmitted plus, I mean you transmitted the signal here, this signal is transmitted, but because of the wrong decision or the changes in the channel, you have detected it to be -1 +1. So, actually signal transmitted in this coordinate and you have detected that as if this signal is transmitted. So, another is the 1/4 is the probability that you have transmitted these and you have detected this, vice versa you have transmitted this, you have decided this one, or transmitted this and you have decided to be here. Other two is you have transmitted minus plus and you have got here, or you have transmitted minus plus and you have turned to be here. Equivalently, you have transmitted plus minus, you have suddenly been here, you are detecting you are here, or you have transmitted this and you are detecting that as if you are here. So, actually whenever we are writing it, basically the way this probability is written is like this: B1 B2 was actually transmitted, but this is estimated. So, to denote the probability. Next, so we understand actually that instead of writing all these 8 different probabilities, fundamentally we will see that some are there equivalent. For example, probability of finding that two plus signals were transmitted, but wrongly it was detected as double minus, is equivalent that double minus transmitted and detected double plus. Double plus transmitted minus plus is equivalent to double minus detected and the plus minus. Similarly, these two probabilities are also equal. So, hence if I substitute this in this equation of 1.3, in the equation of 1.3, then we will be ending up here. Here actually that whole expression, after substitution of them, we will be ending there with the fact that half of the times, so this minus minus, if it is transmitted, it will be detected as the plus minus, and half of the time the minus, both are the minus transmitted, but detected as the double plus, and plus other two terms are like this, that it is minus plus transmitted but detected as plus 1, and half of the time minus plus transmitted but detected as the plus 1, both are plus 1s. That this minimum distance detector outputs the pair, this it is actually the detector is actually finally give you the pair, estimated detected pair that belongs to this minus 1 and the plus 1, and that maximizes now that big omega function once again. Given this to D1 and D2 to this transmitted is given by this fact, this expression, and where actually your y1 is fundamentally the a1 b1 plus a2 b2 multiplied with this cross correlation factor and the noise embedded in the noise. Similarly, y2 will be given by this expression 1.7, and we understand that the b1 b2 are the transmitted beats, and n1 n2 are the jointly Gaussian noise zero mean and variance actually sigma square, and this rho is sigma square into rho is will be the correlation factor. Now, see one important thing in this expression of this 1.4, this first term, the probability that observed vector due to this is closest to plus minus, and remember when can it happen, let us first see. So, we transmitted double minus, but we actually detecting that it is plus minus, means we transmitted this, but we are detecting that as if we are here. So, when it can happen only if the observations are very close to plus minus than actually the minus minus. I mean, the due to some reason actually I am detecting that I am here, because it is a detector minimum distance decision region based detector, right. So, he tries to actually find out where the distance is minimum. If your detected symbol is such that its distance from here to here and from here to here, if I try to compare it minimal distance from the detected symbol to the plus minus zone, if this distance is close, then he will detect that as if the transmitted signal is plus minus instead of minus minus. So, the decision is becoming wrong, because actually your detected signal is or the received signal is fundamentally close to this zone, it is not close to the double minus zone or the quadrature the quadrature number 4. And that is the only reason why actually this first term will come into picture, which is a wrong decision. First wrong decision will come into the picture, and this situation is accordingly leading us to the fact that the probability of double minus transmitted but received plus minus, it is actually the less than to the probability that double minus you transmitted this omega bigger omega for the 2 number of the users with double minus is less than the plus minus given actually you have transmitted the double minus. So, note that here this equality does not hold good, because this observation could be closer to plus minus than to minus minus, but yet fall in the minimum distance region of either plus plus or this minus plus. So, another way to visualize it is something like this. In the figure we have shown that this is the zone, right. Actually this is a boundary zone of the decision, and so you try to see here and map it like this. In the figure 1, the region that the region of this double minus, it is less than the plus minus, it is just a half plane of this right of the line that bisects the segment between this and this. So, this half plane contains the whole minimum distance region of this plus minus in the figure. So, it is now easy to evaluate, means once I actually write down this expression or the concept like this. So, this right side is easy to evaluate, and because this is a one dimensional Gaussian distribution on a semi infinite intervals, and we can easily trace it, and we will be seeing that we can actually easily express this expression or this probability functions by the known q functions. So, now we are here that probability of that capital omega 2 of transmitted double minus is less than equal to this, given that double minus was transmitted, that can be written like this expression, given that y 1 was equal to this and y 2 was transmitted like this. Fundamentally, once we write this expression, basically we are trying to find out whether the probability of n 1 is greater than a 1, and if this is the probability, you can actually justify it by a q function given by the SNR given by a 1 and the noise. Equivalently, when that by going by the same logic, to transmitted double minus, but you are receiving double plus, it is a cross change that can only happen if this is the situation that is happening, and which will lead you directly towards another q function expressions governed by the expression 1.10. And whereas you see actually when we have derived this, we have utilized the fact because that the random variable a 1 n 1 plus a 2 n 2, where actually this is the equation where probability that this is coming greater than this whole quantity, it is a zero mean Gaussian, and where the variance will be governed by this. So, the variance of this total signal is coming as a power of the transmitted power of the signal section, and this is the variance of the power spectral density of the noise. So, given the power spectral density of the noise, you will be ending up with the variance of this a 1 n 1 plus a 2 n 2, and so finally, the q function will be governed by this expression. Next is the third term, where similarly for minus plus transmitted and plus minus you are ending up with will be again with a another Q function where this is the variance of the another terms of A1 N1 plus A2 N2, A1 N1 minus A2 N2, and this is actually minus plus transmitted, but ending up with the double plus. It will be also given by the another Q function. So, if I substitute all these values in the fundamental expression of this probability of getting error, we will be ending up with the equation 1.13, where 2 times we got this Q function of A1 by sigma. So, that is why that term is coming is a Q of A1 by sigma, other terms are remaining with the corresponding multiplication of half. So, this last term in this equation, it is redundant, it will be if my rho is greater than equal to 0. Equivalently, this term will be redundant if my rho is less than equal to 0. So, accordingly actually you for which zone of the SNR you are dealing with, based on that you can either discard the second term or the third term, and the calculation of the error probability will be ending up with the any two terms over the zone of the operation. So, that can be also expressed by the figure, and finally, actually we are ending up where we are ending up with the fact that if I am interested over the rho less than 0. So, that rho less than 0 is a situation that where the cross correlation values will be actually are basically the cross correlation values are very low, and in that situation we can finally ending up with the fact that the probability of error for the user number 1 will be basically given by these two terms, which are coming from the fact that you are here. Okay. Now, this is the upper term, and so it is how we are going ahead. So, you are upper bounded by this. So, the expression he is saying that there is a maximum possibility of the errors possible given by the whole expression. So, this is the upper bound as if on the minimum distance based error calculated in the optimum multi-user detector. And now, the task is to give the lower bound also on the minimum error probability for this user 1. And we assume that the receiver has some side information now, otherwise actually computation of the lower bound is not feasible, and this side information is related to the transmitted bits, but not available to the original. It is some side information about the transmitted bits are there. So, we will consider the 3 different situations where to calculate this different lower bounds. First condition is that we assume that the receiver is informed about the value of this bit 2. So, we understand actually what the bit 2 is transmitted at this moment, and this is a bit transmitted by the user number 2, whereas I am interested to compute the error probability of user 1. So, the now condition is something like that, you compute the lower bound on the error probability of user 1 given the information about the bit 2, which is the user 2's transmitted bit. So, the best strategy is what? Best strategy is that as B1 and B2 and the noise all are independent of each other. So, I can subtract the component related to the B2, I mean A2 B2 S2T, you subtract it from the received signal, and you will be ending up with a simple the contribution of the noise associated with the contribution of the user 1 or intended users, and this one is a very easy conventional user structure, and we can approximate the error probability by the Q function given by A1 by sigma. Alternatively, if the receiver knows whether the transmitted bits are equal or not. So, he does not know what exactly B2 transmitted, but he understands actually some information is there which says that the transmitted bits are equal or if they are not equal. If they are equal, then the receiver knows whether the B1 B2 is equal to +1 or it is -1 Then the receiver either gets the full information or has a solve binary hypothesis testing given by this. The probability of error in such situation also can be finally found in the form of a Q function given in the equation 1.16 with the side information that the bits are equal, and where the factors of this half, it accounts of the probability that the transmitted bits are different, they are not equal, and the Q function will be in that situation equivalent to the mod x 1 by sigma. The symmetric counterpart of it is to the immediate previous case reveals the fact that the true transmitted bits in this case, they are the different. If they are different, in that situation the minimum error probability will be given by the Q function like this. So, by getting all this inference, we can find out, we are now ready with to find out the lower bound on the minimum error probability. Along with the upper bound already computed by 1.15. So, which results in that the maximum of this of finding out these two Q functions is equivalently actually will be the maximum of all this will be less than equal to the error probability of the user 1, and error probability of the user 1 is given by the expression 1.17. And if I try to plot now the single user mass filter detector output along with this newly computed two lower bound and the upper bound error probabilities, we will be ending up with the figure that is shown in the figure number 3, where this graph A is talking about the single user match filter detector output, and this B is actually showing you the upper bound you have computed, C is the lower bound that we have computed, and we can see that there is not much difference between the upper bound as well as the lower bound that we have computed over the for the optimal multi user detectors for a 2 user case. And so, at a very low SNR, what we see, the very low SNR, we can see that the single user match filter error is the minimum. It is better to use a single user match filter at a low SNR zone. Its performance is far better compared to this other two, and both the arguments of this Q function that we have found in the equation 1.16 as well as 1.17, they are dominated by the term when the by the same term as the sigma tends to 0. Sigma tends to 0 means you are actually in a very high SNR zone, and that is dominated by the multi-user expression, multi-user interference, and both the terms are almost performing the same, the upper bound and the lower bound same merge. And we can actually have a relative ratio of this upper bound to the lower bound. It follows from the fact this ratio of this upper bound to the lower bound, it will converge to 1 unless both the arguments are identical, and if they are not, and if the A2 and A1 are related by this expression, then the ratio will converge to approximately 1.5. So, this is a learning about the 2 user case. Using the 2 users, we have tried to finally calculate the error probability and tried to analyze, and we have understood that error probability calculation involves the integration over a 2D Gaussian probability, and which does not lead us to a closed form expression like the nice Q function expression we see for the single user cases. That is why we are not ending up there. We prefer to go ahead with giving a bound over the probability or upper bound as well as a lower bound on the error probability calculation. That is the way we have derived, and we have seen that in the lower SNR zone these bounds are having some effect, they are different from each other, but as the sigma tends to infinity, I mean noise effect reduces for the higher SNR zone, they both the bounds merge. Moreover, we also see that for a very low SNR zone, that means when the sigma tends to infinity, and sigma tends to infinity, in such situation the multi-user the single user match filter output performs the best compared to the other two bounds, and so the final conclusion should be that if you are working in a noise dominating zone, you should rely on or that architecture should go back to the match filter single user match filter based architecture rather than the joint optimal decision decision strategy that we have discussed for this optimum multi-user detection.